The dependency inversion principle is directly related to the open-closed principle. It says that we should depend on abstractions rather than concretions. Martin puts it more bluntly in the text of his article. Every dependency in the design should target an interface or an abstract class. No dependency should target a concrete class. Here's an example from Martin's paper. This is a standard procedural architecture. Sometimes it's called a call and return architecture. This is the architecture that's most commonly used in non-object-oriented languages like C. The main module depends on mid-level modules that in turn depend on more detailed modules. The problem is that if something in the detailed modules change, those changes run the risk of affecting everything that depends on them. So if the last detail module in this architecture has to be modified for any reason, that change can have an effect on the mid-level module mid-3. And if the mid-level module mid-3 has to change, that in turn could affect the main module. But this shouldn't have to be the case. Typically, a module only needs to rely on certain essential behavior from another module it depends on. The details of how that behavior is implemented should be hidden from the module that uses it. Here's an object-oriented architecture that conforms to the dependency inversion principle. The high-level module depends on other modules, but it only depends on their abstract behavior. If we needed to change the implementation for one of those modules, we could do so without affecting the high-level module, as long as our new implementation satisfies the behavioral abstraction we originally created. In a design by contract sense, the abstraction is our contract. The client, which in this case is the high-level module, knows that any component it uses is going to conform to its abstraction. And the implementer of the component knows that the implementation is going to have to obey the contract that is described by that abstraction. This is a good place to take a little diversion into software components. In this course, we're using modules and components more or less interchangeably. But some software developers who specialize in component-based software engineering think of components in a very specific sense. We touched on some of the qualities of a component at the beginning of this module. It should be deployable, replaceable, and it should have an interface. Many years ago, I was reading an article about software components from an online magazine. It was a discussion about components from two important researchers of component-based systems. Bertrand Meyer, who popularized the notion of design by contract, and Clemens Sikorsky, a Microsoft researcher who wrote a seminal book on component technology. In their back-and-forth discussion, they seemed to be having problems agreeing on the properties that a component should have. Finally, Meyer proposed a starting point. He said that a component should be usable solely on the basis of its specification. That means that if you want to use a software component, you should be able to do so simply by looking at its specification. You shouldn't have to look at how it's implemented. For example, if I want to use a Java list component, I'm not going to look at its code. I'm just going to look at the Java doc. And I'm going to assume that whoever implemented the list, regardless of whether they used an array list or a linked list, I'm going to assume that they implemented it in accordance with the description in Java's API for list. When you talk about the specification of a component, you're not just talking about its interface. The interface is going to help the compiler ensure that the implementation is consistent with the method signatures. However, as a programmer, as a developer, You want to make sure that the component will behave in the way its documentation tells you it'll behave. And the method signatures alone can't tell you that. So let me quickly give you an overview of this. A software component has a specification, something that tells you how the component is going to behave. And it also has an implementation, the code that makes the component behave that way. The specification is an abstraction in the sense of the dependency inversion principle, and the implementation is a concretion. The motivation for software components comes from hardware components. The idea is that as long as two component parts do the same thing and meet the same physical specification, they can be used interchangeably in your system. That is, their functional behavior will be the same. It's still possible there may be a difference in quality, performance, or price, but what they do, the service they provide, will be equivalent. The same applies to software. If I'm building a component, I'm first going to create a specification for that component. For example, if I'm using Java, I'm going to create an interface for the component, and I'm going to write Java docs for that interface. Having an interface allows me to swap out different implementations for the component without breaking client code. And having Java docs lets clients know how the component is supposed to behave. So in a language like Java, I consider both the interface and the Java doc as being essential to the specification. Okay, so now that I have a specification for my component, I want to implement it. Now, of course, the person who writes the specification does not necessarily need to be the same person who writes the implementation, but that's another issue. Okay, so assume I want to implement my specification. In order to do that, I'm going to need to use other components. And if I give you 5 seconds, can you tell me what I need from the components I'll be using? In other words, do I need their interface, their documentation, or do I need their implementation? 5 seconds starting now. The answer is I need their specifications, which in terms of a language like Java means the interface and its documentation. I do not need the implementation. That's something that is subject to change. Okay, so this slide simply shows you how you should be able to swap out different implementations for the same specification without breaking any of the components that depend on your component. We know from previous lectures that software is going to change. Change is inevitable in software engineering. But we want to make sure we can localize the effects of change. If one part of the system needs to change, we don't want to have to re-implement the entire system. The approach of re-implementing the entire system might be fine if you're working on your own pet project where you're the sole developer, but it simply won't scale to larger systems that are software engineered. In a later module, we'll talk a little bit about formal verification. For modular reasoning to work, we have to make sure that the implementation of a component is correct with respect to its specification. Typically, this is done through testing, like unit testing. But there's another way of doing this, and that is by formal verification. Verification tools are still relatively rare in software engineering, but it's a technique that's gaining ground for some certain kinds of software. One last thing I want to mention about the dependency inversion principle. Remember that it says depend on abstractions rather than concretions. The reason this works is because our abstractions are relatively stable. Once we create an abstraction, the idea or hope is that we're not going to modify that abstraction very much. Concretions or implementations are more flexible. We can swap them out or make new ones or perform bug fixes on them. As long as they satisfy their specifications, we're okay. And as long as those specifications don't change, the client using the component will be okay too. The interface segregation principle says that if you have many clients for your component, you should consider having multiple interfaces rather than just one interface. In almost every object-oriented language, even those with single inheritance like Java, you can implement multiple interfaces so that you can apply the interface segregation principle in any OO language. Remember that an interface is a completely abstract class with only method signatures and no implementations. Here's a diagram of what this would look like. Multiple clients use the same service, but they use it in different ways. Instead of having one big interface, you have multiple interfaces geared towards the type of client you're serving. Now, this doesn't mean you're going to have a different interface for every single client. That's going to be impractical, and it would violate all kinds of principles of good design. But the idea is that you might anticipate different categories of clients and have an interface for each type of client. Now, in my opinion, you have to be a bit careful with this principle. It isn't always obvious when you want to split up your interface and create multiple interfaces. I would suggest that if you don't have a very good reason to do this, don't. And even then, see if it makes sense to have multiple components, each with their own interface, rather than have a single monolithic component with multiple interfaces. Okay, that concludes our discussion about the basic object-oriented component principles. In the next video, we'll look at cohesion and coupling, and we'll revisit Martin's paper to see what he has to say about them.